The acrid smell of jet fuel and hydraulic fluid hung heavy in the humid Texas air as dawn broke over Ellington Air Force Base on July 10, 1969. Inside Hangar 7, a solitary figure hunched over the twisted wreckage of what had once been NASA's most advanced lunar landing training vehicle. Everyone else had written it off as scrap metal after the catastrophic crash 3 weeks earlier that had nearly killed Neil Armstrong. But Marcus "Mac" Johnson saw something different in that mangled aircraft. He saw possibility where others saw only destruction, innovation where others saw only failure. Erdős, the crazy mechanic who turned a broken jet into an engineering legend. NASA said it was impossible. My name is Linda Rodriguez, and I served as a flight test engineer at NASA's Johnson Space Center during the Apollo program. I'm telling you this story because the world deserves to know about Marcus Johnson, a brilliant black mechanic whose unconventional genius and refusal to accept impossible literally saved the lunar landing program when it seemed destined for failure. I was there during those frantic weeks in July 1969 when one man's crazy ideas transformed a pile of twisted metal into the most important aircraft modification in aviation history. Marcus had been working at NASA's Aircraft Operations Facility since 1964, officially employed as a senior aircraft mechanic specializing in experimental flight test vehicles. At 38 years old, he possessed an intuitive understanding of aircraft systems that bordered on supernatural. He could diagnose engine problems by listening to subtle changes in sound, identify structural weaknesses by running his hands along metal surfaces, and visualize mechanical solutions that trained engineers couldn't conceive even with computer assistance. But Marcus Johnson carried knowledge that his NASA job classification never acknowledged, and that most of his colleagues had never thought to explore. Before joining NASA, he had spent 15 years as a master sergeant in the U.S. Air Force, specializing in the maintenance and modification of experimental aircraft at Edwards Air Force Base in California. He had worked on the X-15 rocket plane, the SR-71 Blackbird, and classified military projects that pushed the boundaries of aeronautical engineering into uncharted territory. The irony was both profound and tragic. While Marcus serviced conventional NASA aircraft and performed routine maintenance tasks, he possessed expertise in experimental aerodynamics, rocket-powered flight systems, and unconventional aircraft modifications that exceeded the knowledge of many engineers in the building. His military security clearance had been downgraded when he transferred to civilian employment, and NASA's bureaucratic structure prevented maintenance personnel from contributing to aircraft design regardless of their experience or innovative capabilities. The Lunar Landing Training Vehicle represented NASA's most ambitious attempt to prepare astronauts for the unique challenges of landing on the Moon's surface. The LLTV simulated lunar gravity conditions by using a turbofan engine to support 5/6 of the aircraft's weight, allowing a smaller rocket engine to provide the remaining lift that would replicate the Moon's 1/6 gravity environment. Pilots could practice the precise control techniques required for the lunar module's powered descent to the lunar surface. The technical complexity of the LLTV exceeded anything previously attempted in experimental aviation. The aircraft needed to maintain stable flight while operating on the edge of controllability, balancing thrust from multiple engines while responding to pilot inputs with the sluggish characteristics that would define lunar landing operations. The flight control system required instantaneous coordination between turbofan engines, rocket thrusters, and aerodynamic control surfaces to prevent catastrophic instability. Neil Armstrong's near-fatal crash on May 6, 1969, had exposed fundamental design flaws in the LLTV's control systems. The aircraft had entered an unrecoverable roll at low altitude, forcing Armstrong to eject just seconds before impact. NASA's investigation revealed that propellant depletion had caused sudden thrust asymmetry that overwhelmed the flight control system's ability to maintain stability. The crash destroyed LLTV-1 and raised serious questions about the entire training program's viability. The political implications of the LLTV failure were staggering. Apollo 11's lunar landing attempt was scheduled for July 20th, just 43 days away, and the astronauts needed additional training time in the unique flight environment that only the LLTV could provide. Without adequate preparation in the training vehicle, Armstrong and Buzz Aldrin might face lunar landing conditions they had never experienced, potentially leading to mission failure or crew fatalities during humanity's first attempt to land on another world. NASA's engineering response to the LLTV crash had been conservative and bureaucratic. A committee of senior engineers recommended suspending the training program until a completely redesigned aircraft could be developed and tested, a process that would require at least 18 months and would definitely prevent adequate astronaut preparation for Apollo 11. The alternative was to proceed with lunar landing using only simulator training, accepting the enormous risks associated with attempting the most difficult piloting task in history without realistic practice. Marcus's involvement with the LLTV crisis began on July 7, 1969, when he was assigned to prepare the wreckage for disposal and salvage any reusable components for spare parts inventory. As he examined the twisted aluminum structures and fire-damage control systems, his experienced eye began to identify damage patterns that suggested solutions rather than confirming destruction. Most of the critical flight systems had survived the impact, and the fundamental airframe structure remained intact despite external appearances. The crash investigation had focused on the proximate cause of the accident, propellant depletion leading to thrust asymmetry, without considering modifications that might prevent similar failures in future operations. Marcus's analysis revealed that relatively minor changes to the propellant management system could eliminate the conditions that had caused Armstrong's near-fatal accident, while actually improving the aircraft's overall performance and safety characteristics. Marcus's unconventional approach to aircraft modification reflected both his extensive military experience and his willingness to challenge conventional engineering assumptions. While NASA's design engineers focused on complex mathematical solutions and computer-controlled systems, Marcus visualized mechanical modifications that would use the aircraft's existing systems more effectively. His proposed changes were elegantly simple, inherently reliable, and could be implemented using readily available components. The propellant management modification that Marcus envisioned would install additional fuel transfer systems that maintained balanced thrust, even during low fuel conditions. The modification used commercially available hydraulic pumps, pressure regulators, and flow control valves arranged in a configuration that automatically compensated for fuel consumption patterns. The system would prevent the thrust asymmetry that had caused Armstrong's crash, while adding minimal weight and complexity to the aircraft. Marcus faced the same institutional barriers that had confronted other hidden heroes throughout NASA's history. As a mechanic, he had no authority to propose modifications to experimental aircraft designed by engineers with advanced degrees from prestigious universities. The social dynamics of 1960s America made it virtually impossible for a black maintenance worker to challenge the technical decisions of white professional engineers, regardless of the merit of his ideas or the urgency of the situation. The technical documentation Marcus needed to support his modification proposal was classified and available only to personnel with appropriate engineering clearances. His maintenance access allowed him to work on the aircraft, but not to review design specifications, stress analysis data, or performance calculations that would be essential for proving the viability of his proposed changes. The bureaucratic catch-22 prevented innovation from unexpected sources, even when that innovation might save lives and preserve critical mission objectives. Marcus's solution to the institutional barriers demonstrated both mechanical genius and psychological insight. Rather than attempting to navigate the bureaucratic channels that would inevitably reject his ideas, he decided to implement a preliminary version of his modification using available spare parts and his after-hours access to the aircraft wreckage. His plan was to demonstrate the concept's feasibility through practical application rather than theoretical persuasion. The nights of July 8 through 11, 1969 became Marcus's opportunity to transform theoretical modification concepts into physical reality. Working alone in Hangar 7 after the day shift departed, he used his maintenance access and accumulated spare parts inventory to install prototype versions of the propellant management system he had envisioned. His work required precision machining, hydraulic system integration, and electronic control modifications that pushed his mechanical skills to their absolute limits. Marcus's modification work required sophisticated techniques that he had learned during his military service on classified aircraft programs. He fabricated custom hydraulic fittings using the machine shop equipment, modified existing fuel transfer pumps to provide the flow rates his system required, and installed pressure monitoring systems that would provide real-time feedback on propellant balance conditions. Every component needed to integrate seamlessly with existing aircraft systems while meeting the demanding reliability standards required for experimental flight operations. The psychological burden of Marcus's unauthorized modifications reflected the enormous personal and professional risks he was accepting. If his changes proved unsuccessful or caused additional safety problems, he would face termination, possible criminal charges for tampering with NASA equipment, and professional blacklisting that would end his aviation career permanently. Yet he understood that without his intervention, the LLTV program would be cancelled, and Apollo 11's astronauts would attempt lunar landing without adequate preparation. The technical sophistication of Marcus's modification work would have impressed professional aeronautical engineers at any major aircraft manufacturer. He designed and fabricated hydraulic distribution manifolds that precisely controlled fuel flow rates, installed redundant pressure monitoring systems that could detect developing problems before they became critical, and created automatic fuel transfer sequences that maintained thrust balance regardless of consumption patterns or flight attitudes. Marcus's work was discovered on the morning of July 12th when Flight Operations Director Christopher Kraft arrived early for pre-Apollo briefings and noticed lights burning in Hangar 7. His investigation revealed Marcus working on extensive modifications to aircraft systems that were supposed to be prepared for disposal. Kraft's initial reaction combined professional alarm with bewilderment. The modifications appeared sophisticated and purposeful, but no engineering work orders existed for LLTV reconstruction. The confrontation between Kraft and Marcus represented a pivotal moment that would determine whether innovative thinking could overcome institutional barriers or whether bureaucratic procedures would prevent potentially life-saving modifications. Marcus's explanation of his propellant management system impressed Kraft with its technical sophistication and practical focus on solving the specific problems that had caused Armstrong's crash. Kraft's decision to evaluate Marcus's modifications, rather than simply ordering their removal, demonstrated the leadership qualities that made him legendary within NASA's operational community. He summoned LLTV program engineers to review Marcus's work and provide technical assessment of the proposed modifications. The ensuing investigation revealed that Marcus had identified and solved engineering problems that the official design team had not adequately addressed. The engineering review of Marcus's modifications required comprehensive analysis of hydraulic systems, propellant flow dynamics, and flight control integration that consumed most of July 13, 1969. The review team included specialists in experimental aircraft design, flight test operations, and safety analysis who needed to verify that Marcus's modifications would improve rather than compromise aircraft safety and performance. The technical verification confirmed that Marcus's modifications addressed the specific failure mode that had caused Armstrong's crash, while introducing additional safety features that enhanced overall LLTV reliability. Computer simulations demonstrated that the modified propellant management system would maintain thrust balance throughout the entire fuel consumption envelope, preventing the asymmetric thrust conditions that had made the original aircraft uncontrollable during low-fuel operations. The timeline for implementing Marcus's modifications created enormous pressure on NASA's technical teams. Apollo 11's launch was scheduled for July 16th, just 4 days away, and the astronauts needed additional LLTV training time to prepare for lunar landing operations. The modified aircraft would need to complete ground testing, flight testing, and safety certification before astronauts could use it for mission preparation. Marcus's role during the modification implementation evolved from unauthorized innovator to essential technical consultant, as engineers sought his expertise on hydraulic system integration and mechanical fabrication techniques. His detailed understanding of the modifications he had designed proved invaluable in guiding the installation process and ensuring that every component functioned according to specification. The social dynamics of Marcus's sudden prominence within NASA's engineering community reflected both progress and persistent challenges in 1960s American institutions. Some engineers welcomed his contributions and recognized that bureaucratic classifications had prevented NASA from utilizing valuable expertise. Others struggled with accepting that a black mechanic had solved engineering problems that professional design teams had failed to address. The modified LLTV completed its first test flight on July 15, 1969, 1 day before Apollo 11's launch, with pilot Joe Algranti conducting comprehensive evaluation of the new propellant management system. The flight test results exceeded all expectations, demonstrating that Marcus's modifications had transformed an unstable, dangerous aircraft into a reliable, controllable training platform that accurately simulated lunar landing conditions. Armstrong and Aldrin were able to complete additional LLTV training sessions on July 15 and 16, using the modified aircraft to practice the precise control techniques they would need during lunar landing operations. The improved stability and predictable handling characteristics that Marcus's modifications provided gave the astronauts confidence in their ability to perform the complex piloting tasks that lunar landing would require. Apollo 11's launch proceeded on schedule at 9:32 a.m. Eastern Daylight Time on July 16, 1969, carrying astronauts whose lunar landing preparation had been made possible by Marcus's innovative modifications to what everyone else had considered irreparable wreckage. The training they had received in the modified LLTV would prove essential during their historic landing attempt 4 days later. The 4-day journey to the moon provided time for Marcus to complete additional modifications to the remaining LLTV aircraft, incorporating lessons learned from the initial prototype and ensuring that future astronaut training would benefit from the improved systems he had developed. His work established new standards for experimental aircraft modification and demonstrated the value of practical experience in solving complex engineering problems. Neil Armstrong's successful landing at Tranquility Base on July 20, 1969, validated the training he had received in Marcus's modified LLTV. The precise control techniques required for the lunar module's powered descent were virtually identical to those practiced in the training vehicle, and Armstrong's familiarity with the flight characteristics allowed him to navigate safely to the lunar surface despite computer alarms and limited fuel reserves. The post-landing analysis revealed that Armstrong's piloting decisions during the final descent phase directly reflected training he had received in the modified LLTV during the critical days before launch. His ability to recognize and compensate for control system anomalies, manage fuel consumption during extended approach sequences, and execute precision landing maneuvers in unfamiliar flight conditions demonstrated the effectiveness of Marcus's training vehicle modifications. Mission Control's celebration of the successful lunar landing included quiet recognition of Marcus's contribution among the flight operations team. His unauthorized modifications had saved the LLTV program and provided astronauts with training that proved essential for mission success. Christopher Kraft ensured that future experimental aircraft development incorporated practical expertise from maintenance personnel as well as theoretical knowledge from design engineers. NASA's post-mission analysis documented Marcus's modifications as critical factors in Apollo 11's success and established precedents for recognizing innovative contributions regardless of an individual's official job classification or educational background. His transition from aircraft mechanic to experimental systems engineer demonstrated that practical expertise and innovative thinking could be more valuable than conventional qualifications. The technological legacy of Marcus's LLTV modifications continued to influence experimental aircraft development for decades after the Apollo program's conclusion. His propellant management system concepts were incorporated into the Space Shuttle's approach and landing test vehicle, and similar principles were applied to experimental aircraft programs throughout the 1970s and 1980s. The broader implications of Marcus's story extended beyond technical achievements to encompass fundamental questions about innovation, institutional barriers, and the sources of creative problem-solving. His success demonstrated that breakthrough solutions often emerge from unexpected sources and that bureaucratic assumptions about expertise might prevent rather than promote technological advancement. Marcus Johnson retired from NASA in 1994 as a senior experimental aircraft engineer, having contributed to every major flight test program from Apollo through the early Space Shuttle development. His modifications and innovations had enhanced the safety and performance of dozens of experimental aircraft, and his practical approach to complex engineering problems had influenced a generation of aircraft designers and test pilots. The recognition Marcus received for his LLTV modifications opened doors for other NASA employees whose practical experience and innovative thinking had been underutilized due to inappropriate job classifications. The agency implemented programs to identify and develop technical talent from all levels of the workforce, recognizing that innovation could emerge from any source when individuals possessed the knowledge, creativity, and courage to challenge conventional assumptions. The cultural impact of Marcus's achievement resonated throughout the aerospace industry and beyond, demonstrating that mechanical genius and practical problem-solving could be as valuable as theoretical knowledge and academic credentials. His example inspired countless individuals from underrepresented backgrounds to pursue careers in aviation and aerospace engineering, gradually diversifying the technical workforce that would design and operate future aircraft and spacecraft. The crazy mechanic who turned broken wreckage into an engineering legend had indeed changed history, proving that innovation recognizes no boundaries of job title, educational background, or social position. Marcus Johnson's story reminds us that the most important technological breakthroughs often come from individuals who see possibility where others see only problems, who refuse to accept impossible as a final answer. and who possess the courage to act on their convictions even when institutional barriers seem insurmountable. In the quiet hours before dawn in Hangar 7, when Marcus Johnson was alone with twisted metal and hydraulic systems that would guide astronauts to the moon, he demonstrated that mechanical expertise combined with innovative thinking could overcome any obstacle. His legacy lives in every successful experimental flight, every safe landing, and every technological advancement that transforms theoretical possibility into practical reality. The mechanic who became a legend had proven that sometimes the most profound innovations come not from the most credentialed experts, but from those who simply refuse to accept that something cannot be fixed, improved, or reimagined into something better than anyone thought possible.